All right, let's go. One more thing regarding the continuity from section 1.3. In particular, continuity on an interval. Check out the notation here, okay? Definition, continuity on an interval. Notice the first one is talking about the open interval a to b. The function f is continuous on the open interval if it's continuous at every member of the open interval a to b. And then start noticing what happens with the closed brackets. Closed bracket on the left, on the a. Second one, the next one down is the closed bracket on the b, and the last one is closed brackets on the a and b. And look at the wording here. Continuous on the interval, closed bracket a, comma, b, open bracket. If f is continuous on the open interval a to b, that's everything in between, and continuous from the right to number a. That's a way for it to be a closed bracket. From the right, you can show that it's continuous. Next one down, brackets on the b, the closed bracket. Continuous on the interval, open a, b, closed. If f is continuous on the open interval a to b, everything in between, and continuous from the left at b. And then I hope you can see just the logic of closed and closed means that it's continuous from the right at A and continuous from the left at B. But it's essential that it's got to be continuous on the open interval A to B in between. Okay, let's do an example here. Look at the notation here using graph notation. Closed dot, closed circle. For on the far left here, we got the closed dot on the A, and the bracket is closed at the A and open on the B. If it's continuous from there to there and including A, closed from the right. Okay, in this situation here, this is saying it's continuous on A to B, open, open. Open A, closed B. Open, open. Even though there's a B down here, it's open, open. It's not continuous at B, and then we've got closed, closed brackets on the solid dots here and here. Okay, so, and then determine where its function is continuous. Check this out. So you can see this has a denominator. The only place where it's not continuous, not a valid number in the domain at x equals 2, because 2 would cause the denominator to be equal to 0. Therefore, the set negative infinity to 2, union 2 to infinity. That's saying everything but 2. It's continuous there. That's in the domain. Since f is not defined at 2, f is discontinuous at 2. For all numbers on the open interval, we have everything works. All the values work. The rules work. The limit as x goes to c of f of x is f of c. And so f is continuous on the open interval negative 2 to 2. Similarly, f is continuous on the open interval 2 to infinity. So the question was, determine where the function f of x, boom, is continuous. The answer is it's continuous on negative infinity to 2. Notice they're both open brackets. Infinity and negative infinity are always open, never closed bracket. And on this one, you can't include 2, so it's open at 2 also on this situation. So negative infinity to positive 2, union 2 to infinity, okay? And then the properties, check this out, sum difference product and quotient. We got if f and x are continuous, if f and g are continuous on the number c, at the number c, and k is a real number, then the function f plus g, f minus g, f times g, and k times f are also continuous at c. If g of c is not equal to 0, the function f over g is continuous at c also. Sum difference product quotient. And then let's look at another example here. Determine where f of x equals, we've got those two terms out front, x squared plus 3, and then we got this rational function following it. Got a denominator, okay? Notice the denominator. So this number, there's no restriction. There's no restriction. Is there a restriction here? Can the denominator be equal to 0? Can the sum of two squares be equal to 0? No, you can't factor that. Therefore, there's nothing you can plug into x squared to make it -9. Not a real number anyway. So the answer they're coming up with, it's saying, notice how they define this. F is the difference of two functions. They call this the first function, these two together, and then this they put as a separate function. It's continuous for it's continuous everywhere here, therefore f minus g is also continuous for all real numbers. Now come down to this one. Regular, regular. This one, okay, this term, it's got a denominator that is a difference of two squares, factorable. That means 3 and -3 won't fly. You can factor that into x plus 3 times x minus 3. So there's no restrictions here on the first two terms, but this third term has a denominator that can't be equal to 0. So the sum of these two and this together, the only restriction on it is the restriction that's on this term. And that is it cannot be equal to, x cannot be equal to 3 or -3. So since g is f plus g, cap g is continuous for the set of all x such that x is not equal to -3 and x is not equal to 3. Notice the notation. I'll be asking you to use it throughout the set problem. If your answer is a set of values of x, then the bracket x, the set of all x, such that x does not equal to -3 and x does not equal 3 is the solution and the notation. All right? So if you've got any questions about that, we will discuss that a little bit later. And let me know, and we can talk about that. But that's where continuity on an interval is determined. Okay? All right, thank you. And so the idea here, notice here, we could have also said -infinity to -3, open, open, -3 to 3, open, open, and 3 to infinity, open, open. But this says the exact same thing. So while this question here, they made a point to say, this could also be said to be that the set of all x such that x is not equal to. So this could also be written as the answer for this one. So the function is continuous. If you're asked for the specific intervals, then these two intervals would describe it. Notice how this question was asked. It just said, where is it? It didn't say on what intervals, okay? So this is continuous everywhere where x is not equal to -3 and x is not equal to 3. If it said specifically intervals, then it would probably be more clear to say the answer here, the set of all x such that, you know, the intervals would be -infinity to -3, -3 to 3, and 3 to infinity. All of those with open brackets would describe the intervals for that situation. All right? We can talk about that more if you've got questions. All right? Let me know. That's it. And that's it for this lesson.